Hello, everyone. I'm Esther, and I'll be speaking on when a program type checks. Okay. So to illustrate what I mean by this question, I have a couple motivating examples here. The first example is the identity function applied to the number 0. And those of you familiar with statically typed languages will know that this expression does type check. You have a function, and you're giving it a parameter. Everything works out. In the second example, you have 0 applied to the identity function. So all I did was flip the terms in the expressions. And clearly, this does not type check, because now you have this integer value, and you're trying to give it a parameter, but that doesn't work. So when you see this, it's all very intuitive. But why does the program behave this way? What really says that the first expression should type check and the second one should not? Is it just the arbitrary implementation of the type checker? Is it some set of rules somewhere? So let's start by talking about what a type system is trying to accomplish. The objective of a type system is to guarantee good behavior when your program executes by ruling out certain classes of runtime errors. And by doing this earlier on in the development phase, you get fewer runtime checks, and you also catch these errors sooner. So throughout this talk, let's keep this objective in mind as why we have type systems and what they're designed to do. So in order to ensure that your type system makes the guarantees you want it to, you need a formal specification of the type system. So now I'll be covering how you actually give a spec for what your type system is allowing and not allowing. So type systems are formalized using building blocks called typing judgments. And they come in this format. You have a context gamma, which you can think of as a mapping from variables to types. And then you have this sideways T symbol, which is the entails symbol. And you read it as gamma entails the expression E has type tau. So I'll be getting more into what that means later. Typing judgments can be combined to form typing rules, where you have several typing judgments above the horizontal line as the premises. And this rule says if we can prove the premises, then we can prove the consequent, the conclusion, below the horizontal line. OK, so let's make this clear with an example using simply typed lambda calculus. And I'm sure many of you are familiar with lambda calculus, so I'll just go over this quickly. In the simply typed lambda calculus, you have expressions E, which can be either variables or abstractions, essentially functions taking one parameter. And they can also be applications, some expression applied to another expression. The types in the simply typed lambda calculus are all of the form tau arrow tau. So they're all function types. So let's get into the typing rules. With typing rules, I often find it useful to start from the bottom, what you're trying to prove, and look at the premises to identify what needs to be proved in order to show the conclusion. So in this typing rule for the variable, we have a conclusion of gamma entails x has type tau. And to show this conclusion, you have to know that x has type tau is in your context gamma. But how does x has type tau get into your context to begin with? So this happens in the abstraction rule. For the abstraction, you want to show that lambda x dot e has type tau1 arrow tau2. And in order to show this, you must also be able to prove that E has type tau2 under the context gamma, including the variable x has type tau1. So what you're doing is you're assuming that x has type tau1, and you're adding it to the context, and you're trying to see if E has type tau2 under that environment. And this allows you to use x in the body of E. Lastly, we have the application rule, where you have some expression E2 and another expression E1. And you want to show that E2 applied to E1 has type tau2. And to do this, you have to be able to prove that E2 has type tau1 arrow tau2. So E2 is a function type. And E1 has type tau1. So E1 has the type that you expect as an argument to E2. OK, so how do we use these rules to actually prove the type of an expression? For simplicity, I added built-in natural numbers and a built-in type integer to the lambda calculus. So starting from the bottom up again, we see that what we want to show is that the identity function applied to 0 has type int. And to do this, we apply the application rule. So we want to show that the parameter to our function is of the right type, and we want to show that our function has type tau arrow tau. And then from there, we use the abstraction rule, and then we use the variable rule. So you don't have to understand this whole proof tree now, but this is the kind of proof that you need in order for an expression in your language to type check. OK, so I threw a lot of symbols at you, and now we have a formalization for a language. And hopefully, you understand a little bit about how type systems are defined. But it still seems pretty arbitrary. We still haven't answered the question of why you can apply a function to an argument, but you can't apply an integer to an argument, for instance. So if we think back to the motivation behind type systems, which is guaranteeing good behavior, we remember that actually there are properties we want to prove about our type systems. And one really fundamental property is called type soundness. So type soundness is the formalization of the property for good behavior. You can prove it as long as you have a formalized type system and a semantics for your language. The intuition for what type soundness says is that your program will never behave in an unspecified way. So you won't ever have some execution pattern that you did not specify in your semantics. The formal statement comes in two parts, progress and preservation. Progress states that either your expression is a value or you can keep running it. So you know that you'll never get into a state where you have this program and you don't know how to proceed. The second part is preservation, which says that you have an expression and you can prove that this expression has a certain type. So preservation says if you step this expression, if you reduce it, it'll still have a type. You'll still be able to prove that it has a certain type and that this type will be the same. So in conclusion, a program type checks when you have a formal type system that guarantees that it will be well behaved. So you don't need an implementation of a type checker. You can decouple from that. You can say, I have this specification, my type system follows it, and I can also show this property type soundness, which says that as long as I follow my type system and my semantics, then everything that my program does will be well specified. And this is fundamental to why and how people study type systems. Anytime you have a statically typed language, the objective is to provide safety or to provide soundness. All right. Does anyone have questions?
Why do you say that you don't need a type checker in that situation?
So what you don't need is an implementation of a type checker. The implementation of the type checker really just follows the specification that you outline in the formal type system.
Oh, so if you use the formal specification, therefore, if you use it, then you don't need a type checker.
Yes. So actually, you can study your language entirely theoretically as a paper language just by defining these typing rules and the semantics. And you never need to write any code. Yeah. Yeah. OK. Other questions? OK.